So here we can see the main specification of the transmitter, which we want to implement for the Wi-Fi 3 standard. So you want the transmitter to operate from 2.4 GHz to 2.5 GHz, and the maximum output power should be plus 16 dBm. Now for 54 Mbps data rate, we know that the peak to average power ratio is going to be equal to 9 dB. So we are assuming that the transmitter should have a output referred 1 dB compression point to be at least 25 dBm. So that for the maximum output power, we will be operating at a 9 dB backoff from the 1 dB compression point. We also derived that a transmitter gain of 27 dB will be sufficient to take the signal from the DAC and finally drive the antenna load. So for this case study, we are going to take a 45 nanometer CMOS process, and this process has a core device which is operating at 1.1 volt supply, and also IO devices operating at 2 volt supply. This IO devices we are going to take advantage in trying to design the power amplifier, because this power amplifier has to drive a 16 dBm output power with 25 dBm P1 dB. So the output swing is going to be really high. So the IO devices can help in operating the PA at a higher voltage supply so as to improve the output voltage swing. So we are going to design the front end for this transmitter, so which is going to be the output stage. So for this power amplifier, we will assume that the matching network is off chip, and also there is an off chip balance to convert the differential output of the power amplifier to the single-ended 50 ohms load. We'll be using the 2 volt IO devices as cascode element so as to provide high output voltage swing while protecting the 1.1 volt core device. So we can see that if we are targeting a output 1 dB compression of 25 dBm, so it means that at 50 ohms, this 25 dBm will translate to a voltage amplitude of 5.6 volts. So even though the input signal will rarely go close to 25 dBm, but we have to design the power amplifier such that it can handle such a high swing at the load. Now it is not possible to design power amplifier which can handle such a high voltage swing across the MOS devices. So what we are going to do is, we will be assuming there is an off-chip balance which will be transforming the 50 ohms load to a lower value. Now to find what will be the optimum load for the power amplifier, so we can make some simple design choices. So first of all, we will assume that this input element and the cascode element together will need a 0.6 volt as the minimum drain voltage, where 0.2 volt we are budgeting for the input element and 0.4 volt we are budgeting for the cascode element. In such a scenario, if you are operating the PA with a 2 volt supply, then the minimum voltage which we can achieve at the single-ended output of the PA is going to be 2 minus 0.6 volts, which is 1.4 volts. So it means the power amplifier is going to have a differential amplitude of 2.8 volts, whereas the voltage amplitude at 50 ohms is 5.6 volts. So knowing the voltage swing at the 50 ohm load and on the PA side, we can find out what should be the turns ratio for the balance. Here we can see that this is turning out to be almost 2. So if the turns ratio is 2, it means the reflected load on the PA side is going to be 50 by 4, which will be 12.5 ohms. So we are going to design a PA which will be driving an effective load of 12.5 ohms differential, so that once we connect the off-chip matching network and the balance, it will be able to drive a 50 ohms load. Now we are trying to design this power amplifier for this given specification. And here our main objective is to meet the output P1 dB spec of plus 25 dBm. So first we will instantiate the MOSFET. We are going to choose the minimum channel length. Take a finger width of 1 micron. So the first objective is to find the optimum gate source voltage for this input element so as to get the best linearity. As we have done for the case of the LNA, here also we are going to choose the gate source voltage such that the MOSFET is operating at GM3 equal to 0 operating point. Since we have already done the exercise during the LNA design, we know that if we choose the VGS voltage to be equal to 0.59 for this MOSFET, then the GM3 is going to be close to 0 and we can expect good linearity. One point to note with respect to this GM3 equal to 0 biasing point is that this VGS value is very sensitive to PVT. So due to PVT variation, GM3 value may actually become non-zero. So in such a scenario, we need some calibration technique or some other circuit technique to make sure the MOSFET is still operating close to GM3 equal to 0 bias point. So for now, we will choose the VGS to be equal to 0.59, which corresponds to the GM3 equal to 0 bias point. And we are budgeting a VDS of 0.2 volts for this input element. And under this condition, we'll try to find out what is the VD set value and what is the current in this MOSFET so as to get an idea about the current density. So we can run a DC operating point simulation. We can add the VD set of this device as an output parameter for the simulation. So that we get to know how much headroom we have in the VDS. So here we can see that for this VGS value, the VD set is 115 millivolts. So 200 millivolts has sufficient margin to keep the MOSFET in saturation. We will also add few more operating point parameters. So let's find out the FT. The FT is 72 gigahertz. So you can see that for operation around 2.5 gigahertz, it has good enough FT. Along with that, we have got good VDS margin. Now, next step is to choose the cascode device. So we will be using a 2 volt IO device for cascode. Since this device will be able to handle a higher VDD, it can allow higher voltage swing at the P output while protecting the core device. The downside of using IO device is that the minimum channel length is going to be higher than what we get in the core device. So as a result of which the FT is going to come down, which may make it difficult for the PA to operate at higher frequency. So then accordingly we have to choose the biasing such that the FT of this IO device also is at least 10 times more than the operating frequency so that its parasitics don't severely affect our PA design. So let's instantiate this device. So we need to optimize this cascode voltage such that FT and the VD set of this cascode device is as per our design specifications. Since we know that the DC voltage at this cascode drain is going to be equal to the supply voltage, so we will set the drain voltage of this cascode to be equal to 2 volt, and this gate voltage of the cascode we will try to tune such that we get the required VD set and FT from this cascode device. So if we just run the DC operating point simulation 0, so we can also add more expressions for the operating point parameters of the cascode device. And here we can see that if we have chosen the cascode voltage to be 1 volt, the FT is coming out to be 48 gigahertz and VD set is 206 millivolts. So since we have budgeted a VDS of 0.4 volts for the cascode device, you can see that this VD set is much below the VDS which we have budgeted. Also, its FT is much higher than the operating frequency. So the gate voltage of the cascode device to be 1 volt seems to be a good enough bias voltage, and we can go ahead with this design choice. Now we have chosen the gate voltage and the length of these transistors. We need to now find out what should be the width. So let us first design this cascode single-ended amplifier for 1 milliamp of current, and later we are going to do the node scaling to obtain the required bias current. So let us scale the width of both the MOSFETs such that both of them are going to carry 1 milliamps. Here we can see that it is carrying 32 microamps. So let's call it WM1 with 4 fingers. 2 fingers, let's call this as WM2. So now we can do a sweep of this width of a input element and the cascode element to make sure both of them are carrying 1 milliamps. That can be achieved by just doing a DC sweep analysis. So after optimizing, find that this width should be 6.5 micron and the cascode width should be 8.5 micron. Now we can see that both the MOSFETs are carrying 1 milliamps. So now we can remove this voltage source across the input element which was used for helping in the biasing. So now we can see that both the MOSFETs are carrying almost 1 milliamps and the drain voltage of the input element is close to 200 millivolts. So the DC biasing has been set up properly, and now we need to find out. So now we need to find out what is going to be the linearity for such a simple single-ended cascode amplifier, and also what should be the optimum load for this amplifier so that we can achieve the required P1 dB. So first we are going to connect a inductive load to tune out the parasitic cap. Also, let us also add a parallel capacitor. Let's call it CP. So the idea is to tune the parasitics at the output node so as to find what is the maximum swing we can obtain at the drain of this cascode device. So right now we are not connecting any load. There is just some R out of this cascode amplifier itself, based on which we are going to get this swing at the output node. So for now, let us just choose the CPU to be 1 picofarad. And now we can optimize this LP so as to get the maximum gain at the center frequency. For this, we need to perform a AC analysis. So let's try to optimize the value of LP at 2.45 gigahertz. And let us also add a small signal source. Just keep in mind that this LP and CP which we are adding is not any on-chip element. Right now we just want to find out the swing at the output when the output is completely tuned out. So here we can see that at 4.17 nanohenry, the output is completely tuned out. And the CP value also, we have chosen 1 picofarad just so that the LP value will turn out to be some reasonable number. Under this condition, now we want to find out what is the P1 dB compression we can get for this simple cascade amplifier. So for this P1 dB simulation, we need to add a sinusoidal source at the input, and we are going to sweep the power of this large signal sinusoidal source at the input. So it is going to be at center frequency of 2.45 gigahertz, and we are going to sweep the input signal such that it changes in the log scale. So the amplitude is going to be some voltage in dB. So that when we sweep voltage in dB, the amplitude here changes in the linear manner. So for this linearity simulation, again we can use harmonic balance analysis as we did in the case of LNA. So we can add the frequency of the input tone, as well as we can also sweep the power of the input tone. We are sweeping the amplitude of the input tone from -40, -10 with a step size of 5. Now we can plot the compression point for this cascade amplifier. So the output is this Vout node, and we are more interested in the swing at the output. So we want to check what is the output referred 1 dB compression point. So now we can see that as per this plot, the output referred 1 dB compression is coming at 14.3 dBm. So this 14.3 dBm is corresponding to the swing at the output node for a reference impedance of 50 ohms. So the swing which we want at the output is 1.4 volt amplitude. So for 1.4 volt amplitude and a reference impedance of 50 ohms, we find that the corresponding power is 13 dBm. So our target is to make sure the output P1 dB is more than 13 dBm. So here we can see that already we are getting beyond 13 dBm. So we can add this as an output of our analysis. So we can see that it is coming out to be 14.35 dBm output referred P1 dB, and our target output P1 dB is 13 dBm when only considering a 1.4 volt output voltage swing. So in our amplifier, there is no load connected as such, so only the output impedance of this cascade amplifier is giving rise to the voltage swing. So next our job is to add a load to this cascade amplifier and try to see what is the optimum value of RP we can obtain. Let's call it RP. And we know that in the final PA, this RP will be modeling the reflected impedance of the 50 ohms load looking from the PA side. So for now, we are just designing a reference amplifier which is drawing 1 milliamp current, and we want to find what is the optimum load in this case. Later, we are going to do the node scaling to change the output load to the required load of 12.5 ohms differential, which is 6.25 ohms single-handed. So for now, we are going to see if 1 milliamp bias current is set in the amplifier, what should be the RP value. And to get a better idea about what should be the range of RP value, we can find what is the output impedance of this cascade amplifier without this RP. So that can be done by connecting a port to the output node and performing a S parameter simulation. Let us check the output impedance. So we can see that the imaginary part is close to 0 at the operating frequency, whereas the real part is around 29 microsiemens, which corresponds to a resistance of 34 kilo ohms. So this simple simulation tells us that the output impedance of this cascade amplifier is 34 kilo ohms. So if we are going to connect an RP in parallel to this cascade amplifier, the first thing going to happen is the gain of this cascade amplifier is going to reduce. But if we want to improve the efficiency of this amplifier, we want entire channel current to flow to the output load. So for higher efficiency, we want this RP to be as low as possible, whereas for higher gain, we want this RP to be as high as possible. And one downside of having a low gain is that the swing at the input is also going to increase for the same output swing. And because this higher input swing, we may start seeing some nonlinearity because of the GM of this transistor. So there is an optimum value of RP, which will give us the required P1 dB, while also making sure that good amount of this signal current is flowing to the load. So now let us try to find the minimum value of RP, which we can connect here so that we get the maximum efficiency possible, while still making sure that the overall P1 dB of this amplifier is maintained to the required value of 13 dBm as per our output setup. So we are going to do a parametric sweep. Here we are going to sweep the RP. So 34 kilo ohms is the output impedance of the cascade amplifier. So the RP we can keep somewhere around 1/10 of the output impedance. So let us try to find the optimum value. Now we can plot the output referred P1 dB point. So we can see that this point is continuously reducing as the RP is also reducing, which makes sense because at a lower RP, now the gain is going to reduce. So the gate of the input element is going to swing higher, which may add some nonlinearity. But at the same time, lower RP also gives a higher efficiency. So for our application, we need a output referred P1 dB of around 13 dBm, which corresponds to a voltage amplitude of 1.4 volt. So we will choose an RP around 3.7K. So now we can check the various node voltages when we are operating close to the P1 dB. So the input referred P1 dB point is around -24. So we'll check the waveform for input voltage of -24 dB. So we can see that the output voltage is swinging as low as 0.56. So we had busted a total VDS for cascade plus the input element to be 0.6. It is almost touching that limit. And on the higher side, it is going 1.45 volts above the supply. So we can see that this is the kind of voltage swing we are getting at the drain. Now, if you look at the intermediate node is also swinging. So as we can see, the lowest voltage it is going is 105 millivolts. This is the reason why the input element is having some compression issue. So for now, we will go ahead with the design and we will freeze the RP to be 3700 ohms. So since we finally want to drive reflected load of 12.5 ohms differential, which is 6.25 ohms single-ended. So now we can see that we need to scale this cascade amplifier by a large factor. to be able to drive the 6.25 ohms of load. So as per the calculation, it is around 590 times. So this cascade amplifier needs to be increased in size by 590 times so that it can drive a 6.25 ohms load. So we will scale this devices by 590 times, multiplier of 10 here, a multiplier of 10 here, and then we will connect 59 of them in parallel. So now we don't need any extra capacitance because the amplifier itself will be having good amount of parasitic cap. The RP we want to be 6.25 ohms. LP we want to optimize to first tune the amplifier at the operating frequency. So we can see that an LP value of around 1.6 nanohenry is going to do the job. So now we can run a AC simulation in the entire band to check the small signal gain. At the same time, we can also do this compression test to find out if we are getting the required output referred 1 dB compression point. So if we look at the gain, we can see that we are getting a gain of almost 29 dB, which is flat in the entire band. So we can see that the output referred P1 dB is 13 dB when using 50 ohm as a reference impedance. So we can find the output referred P1 dB for our load of 6.25 ohms. So here we will add 6.25 ohms. And then find the output referred P1 dB. So we are getting it to be 22.28 dBm. And since this is only the half circuit, so in the full circuit we'll be having a differential amplifier. So in such a scenario, we will get 22 plus 3 dB, so which will be the 25 dBm output referred P1 dB. So we are meeting the specification for the P1 dB. So now we can just convert this circuit into differential circuit. So now we will be applying a differential input. And here also 0.5 with 180 degree phase shift. For the HB analysis also, we will add a 180 degree phase shift for the input tone. So these inductors are going to be off chip. An inductor and any matching network along with the balance going to be off chip. So right now we are just using ideal inductors here. So now the load is going to become 12.5 ohms. Let's see the small signal gain as well as the compression point for this differential power amplifier. So now we can see that total current coming from the supply is 1.2 amps. It's really very high current. If you look at the small signal gain, it is around 29 dB. So now we can plot the 1 dB compression point for this differential power amplifier. So you can set the load to be 12.5 ohms in the output power format. we can directly choose the differential nets. So here we can see that the output P1 dB is coming somewhere around 25 dBm. So we can see that we are getting a small signal gain of around 29 dB and the output 1 dB compression point of 25 dBm. Now we can also find out what is the efficiency of this power amplifier when it is operating around 1 dB compression point. So to do that, we need to find what is the input power corresponding to the 1 dB compression point. So that power is around minus 18 dBm. Minus 18 dB we are setting as the input voltage level. So we can find out the efficiency by finding out what is the RF power at the load and how much is the power supplied by the DC source. So we can find this power at fundamental to be 388 milliwatt, and similarly we can find the power supplied by the DC source as 2.3 watts, and we can find the efficiency by taking the ratio. The drain efficiency is going to be P out by P supply into 100 when we want the efficiency in percentage. So here we can see that the drain efficiency is 16.5%. This is at the P1 dB point. So here we can see the output power versus the drain efficiency plot. So we are targeting a P1 dB of 25 dBm. So at this P1 dB, we are getting a drain efficiency of around 13%. We'll be having an average output power of around 16 dBm. So we can see that for that value, the efficiency is really low, only some 1.7%. We can see that this drain efficiency is really low. One reason is the gain is very high. So one way to improve the efficiency is by reducing the gain so that more of the signal power is going to the output load. So the retuning of these parameters can be done. So in this design, there are a few caveats. So one important point to note here is that we are assuming an ideal voltage source to drive this power amplifier, which is not true. In reality, this power amplifier will be driven by another driver stage. So the driver will be having a high output impedance to drive these two nodes. Such a scenario, there can be some cases of instability as well. So we need to thoroughly simulate the stability of power amplifiers also. And in reality, so this output will be going off chip, and when the signal goes off chip, there will be package parasitics. So this package parasitics and finally the output balance and the matching network, all those components will be adding their own loss. So we are going to see even reduced efficiency. So there is one more type of analysis called load pull analysis, which is used to optimize the load seen by the power amplifier, which can give the either best efficiency or the best linearity. Here in this simple design exercise, we have only used the harmonic balance and the other small signal simulations. This design can be used as a first cut output stage. Then this design can be further tuned to improve efficiency while maintaining the linearity.